The universe expands, yet the truth remains, still within.
Why does the universe exist at all? Before asking how the universe works, there is a far more unsettling question that science continues to confront. Why does the universe exist at all? It may sound like a philosophical curiosity rather than a scientific problem, but the deeper physics advances, the more this question becomes unavoidable. For centuries, scientists focused on describing the laws that govern reality. Gravity explains the motion of planets. Electromagnetism explains light and electricity. Quantum mechanics describes the strange behavior of particles at the smallest scales. These theories have been remarkably successful. They allow us to predict the motion of galaxies, build technologies that power our world, and probe the earliest moments of cosmic history. Yet all of these explanations assume something that is rarely questioned: the existence of the universe itself. Physics explains how things behave once the universe exists. It does not easily explain why there is something rather than nothing. The modern scientific story of the cosmos begins with the Big Bang. According to current cosmology, the universe began approximately 13.8 billion years ago in an extremely hot, dense state. Space itself began expanding, and as the universe cooled, particles formed, atoms emerged, stars ignited, and galaxies assembled into the vast cosmic structures we observe today. But the Big Bang Theory describes the evolution of the universe after its earliest moment. It does not fully explain why the universe began in the first place. For a long time, scientists believed that answering this question might simply be impossible. Perhaps the universe just exists as a brute fact, something that requires no deeper explanation. But modern physics has begun exploring possibilities that challenge this assumption. One idea comes from quantum mechanics. In quantum theory, the concept of nothing is far more complicated than it appears. In everyday language, nothing means the complete absence of everything. But in quantum physics, empty space, the vacuum, is not truly empty. Instead, it is filled with fluctuating quantum fields that constantly generate tiny bursts of energy. Particles can spontaneously appear and disappear in these fluctuations. These events are incredibly small and short-lived, but they are measurable. Even in the emptiest region of space, the quantum vacuum is never perfectly still. This strange property of quantum mechanics has led some physicists to propose a radical possibility. The universe itself may have emerged from a quantum fluctuation. According to certain cosmological models, if space and time themselves are subject to quantum behavior, then under the right conditions, a small region of space could spontaneously form and begin expanding. In this scenario, The universe does not require an external trigger. The laws of physics themselves allow the spontaneous creation of space-time. This idea sounds extraordinary, yet it is taken seriously in theoretical physics. Another perspective comes from the concept of inflation. Shortly after the Big Bang, the universe appears to have undergone a brief but extremely rapid expansion, known as cosmic inflation. During this fraction of a second, space expanded faster than the speed of light, smoothing out irregularities and shaping the large-scale structure of the cosmos. Some theories suggest that inflation may not have occurred only once. Instead, inflation may happen repeatedly, creating multiple expanding regions of space-time. Each region could become its own universe with its own physical conditions. This idea leads to the concept of the multiverse, a vast collection of universes existing beyond the limits of our observable cosmos. If the multiverse exists, our universe may be just one small region within an enormous cosmic landscape. This possibility raises another intriguing idea. The laws of physics themselves might not be unique in different universes. The fundamental constants of nature, the strength of gravity, the mass of particles, the properties of forces, might take different values. Some universes might collapse immediately. Others might expand too quickly for structures to form. Only a small fraction might allow galaxies, stars, and planets to exist. Our universe appears finely tuned for complexity. The laws of physics allow matter to organize into atoms, molecules, stars, and living systems. If the constants of nature were even slightly different, the universe might be completely lifeless. Why are the laws of physics set in exactly the way that allows structure to emerge? Some scientists argue that the answer may lie in probability within a vast multiverse. If many universes exist with different conditions, it is not surprising that at least one universe, ours, happens to permit the existence of observers. This explanation is known as the anthropic principle. It does not claim that the universe was designed for life. Instead, it suggests that we observe a universe compatible with our existence, simply because we could not exist in any other kind. Still, the question of existence goes even deeper. Modern theoretical physics has begun exploring the possibility that space, time, and matter may not be fundamental at all. Instead, they might emerge from deeper informational structures. Some researchers believe that reality may ultimately be described in terms of information. In this view, the universe resembles a vast network of relationships rather than a collection of objects. Space and time could arise from patterns of interaction within this underlying system. One fascinating development supporting this idea comes from studies of quantum entanglement. Entanglement links particles together in such a way that the state of one particle instantly determines the state of another, even across vast distances. This phenomenon puzzled Einstein, who famously called it spooky action at a distance. But modern research suggests that entanglement may play a fundamental role in shaping the structure of space itself. In certain theoretical models, the geometry of space-time appears to emerge from patterns of quantum entanglement between particles. When entanglement increases, space becomes more connected. When it decreases, space begins to fragment. If this idea is correct, then space may not be a fundamental stage on which reality unfolds. Instead, space may be a consequence of deeper informational relationships. This perspective represents one of the most profound shifts in scientific thinking. For centuries, physics focused on matter moving through space. Today, many physicists suspect that both matter and space may arise from deeper structures that we are only beginning to understand. Even time, which seems so familiar and constant, may not be fundamental. Some theories suggest that time itself could emerge from more basic processes. At the deepest level of reality, there may be no universal flow of time at all. Instead, time might arise from changes in relationships between physical systems. If these ideas prove correct, the universe may be far more abstract than our everyday experience suggests. Reality may not be built from objects, but from patterns. And yet, despite these extraordinary possibilities, one fact remains clear. Science has not yet reached the final explanation of the universe. Every new discovery reveals deeper layers of mystery. Dark matter makes up most of the matter in the universe, yet we do not know what it is. Dark energy drives cosmic expansion, but its nature remains unknown. Quantum mechanics describes the behavior of particles with extraordinary precision, yet its deeper meaning continues to be debated. The universe continues to challenge our understanding, and perhaps that is what makes science so remarkable. The goal of science is not to eliminate mystery, but to explore it. Each new theory expands our knowledge while revealing new questions waiting to be answered. The universe is not a puzzle that can be solved once and for all. It is an ongoing exploration. Every observation, every experiment, every equation brings us closer to understanding the nature of reality, and at the same time reminds us how much remains unknown. In the end, the most profound discovery of science may not be a final answer. It may be the realization that the universe is deeper, richer, and more mysterious than we ever imagined. And the search to understand it continues.